Come here to Papa. Alrighty. 3090 is a beast.
That right there is Jensen Huang. You might know him, might have heard of him. He's CEO of NVIDIA. And yes, you could say that he has quite literally cooked. And the wild part, the reason he can stand there doing that.
Welcome to my kitchen.
It started with a decision made nearly 20 years ago when NVIDIA was genuinely on the ropes.
And I'd never taken a single business class, and I've never taken any marketing classes.
So let's talk about that decision, because it's one of the most fascinating stories in the entire history of modern technology and how we have gotten to where we are today.
I just want everybody in the world to hear that you said, I build bigger things than you do. You do.
So in 1993, three engineers sitting in a Denny's in San Jose, California, Jensen Huang, Chris Malachowski, and Curtis Priam had one very clear idea. Gaming was going to get enormous, and when it did, it was going to need dedicated graphics processors to make those games actually look good. Not the general purpose chips inside your computer, rather something built specifically for rendering images fast. They called the company NVIDIA.
Hello, Austin. It's great to be here. And so let's get started.
They nearly ran out of money in 1995 and got bailed out by SGS Thompson on a deal that, by all accounts, Jensen Huang absolutely hustled his way into. But they survived.
You guessed it!
And by the late 1990s and early 2000s, they were genuinely flying.
Everything you were looking at just now, all of those games were running on the NVIDIA GeForce GTX 1080.
The GeForce brand became almost synonymous with gaming. If you built a gaming PC in the early 2000s, you wanted an NVIDIA graphics card, full stop. And the numbers reflected that. Revenue was climbing. Market share was strong. The company had fought off competitors, survived near bankruptcy, and carved out a genuinely dominant position in PC gaming graphics. By almost any measure, they were a success story. But there was a problem quietly forming underneath all of that. The gaming market was starting to saturate, which sounds obvious in hindsight, but at the time it was genuinely uncomfortable to acknowledge.
Building a company and building a video turned out to have been a million times harder than any of us expected it to be.
There are only so many gamers, and once they all have a graphics card, you're no longer selling to a growing market. Instead, you're selling upgrades. And then there was the bigger threat. Intel and AMD, the companies making the actual processors inside your computer, they were beginning to integrate basic graphics capabilities directly into their chips. Not great graphics, but good enough for a lot of people. For a company whose entire business was making standalone graphics cards, that was a slow-moving but very real existential threat. Now, while NVIDIA was quietly worrying about its future in gaming, a completely separate problem was unfolding in research labs around the world. Scientists, the people doing climate modeling, drug discovery, particle physics, fluid dynamics, were hitting a wall. Moore's law, which had basically promised the computing world that chips would double in power every 2 years, was starting to break down. You simply couldn't keep making individual processors faster without them generating so much heat, they'd effectively destroy themselves. So how do you get more computing power when you can't make a single chip faster? The answer, in theory, was parallel processing. Instead of one incredibly fast chip doing everything in order, you use hundreds or thousands of smaller processors doing many things simultaneously. Think of it like this. If you need to count all the grains of sand on a beach, one person counting is going to take an extraordinarily long time. But if you give a patch of beach each to 10,000 people and have them all count simultaneously, you're done in a fraction of the time. That's the core idea, and it works brilliantly, actually. The problem was most software in the world was written to work in a straight line, one task, then the next, then the next. Rewriting it for parallel processing meant essentially starting from scratch. Now, here's where it gets interesting. A handful of researchers in the mid-2000s started noticing something slightly odd. Graphics cards, the things designed entirely for gaming, were already built to do parallel processing, because that's exactly what rendering a game requires. You're not drawing one pixel at a time, you're instead calculating thousands of pixels simultaneously every single frame, dozens of times per second. A GPU is fundamentally a massively parallel machine, so these researchers started quietly experimenting. Could you repurpose a gaming graphics card to do scientific computing? The answer was yes, but it was absolutely horrible to actually do. The software tools didn't exist. The programming languages weren't designed for it. To run scientific calculations on a gaming GPU in 2005, you basically had to trick the chip into thinking your physics simulation was a texture being rendered, which is a bit like using a Ferrari to deliver pizza. Technically it works, but it's not quite what anyone had in mind, and yet it worked. The results were astonishing. Calculations that had taken hours on traditional processors were completing in minutes. Word started spreading quietly through research communities, and someone at NVIDIA was paying very close attention. In 2006, Jensen Huang and his team made a decision. They were going to take the problem those researchers were wrestling with, and they were going to solve it properly. Not with a hack, not with a workaround, with a proper, fully supported, fully engineered solution. They called it Compute Unified Device Architecture, or CUDA. And the core idea was elegant in its simplicity: make NVIDIA graphics cards programmable for general purpose computing. Give scientists and engineers a proper set of tools, proper programming languages they already knew, proper compilers, proper documentation, so that running calculations on a GPU felt like a natural choice rather than a technical nightmare. To take advantage of this new revolutionary computing pipeline, NVIDIA launched the GeForce 8800 GTX with the introduction of NVIDIA's Tesla architecture. Tailored for high-performance computing, it featured the innovative Tesla Unified Shader architecture, which pivoted away from fixed pipeline chips used in previous gaming cards. This legendary chip instead used hundreds of programmable parallel processing cores. They could dynamically handle any type of shader operation simultaneously, where previously the fixed pipeline of running pixel and vertex shaders separately caused lag or stuttering. And you might have guessed, this new unified architecture coupled with CUDA allowed developers and researchers to harness these massively parallel gaming GPUs for general purpose computing and scientific research. This then gave way for neural network pioneers to train early deep learning models using GPUs instead of traditional sequential CPUs, saving a ton of time which would have otherwise been wasted on, well, just waiting. Now, I want to be clear about what made this genuinely difficult. NVIDIA wasn't doing this because scientists were banging down their door asking for it. They weren't. The scientific computing market, even with CUDA factored in, was tiny. We're talking maybe 1 or 2% of GPU sales. NVIDIA's money came from gamers. And adding CUDA capabilities to their chips meant diverting significant engineering resources away from making their gaming performance better, which was the thing keeping the lights on. So on paper, this looks like a company choosing to invest heavily in a market that barely existed for customers who hadn't asked for it, while their core business was showing signs of pressure. Any sensible analyst at the time would have looked at this and said, absolutely not.
No! No! No!
And honestly, they wouldn't have been being unreasonable. But Jensen Huang had noticed something that the analysts hadn't. Those researchers hacking gaming GPUs in university labs, they weren't doing it because they had nothing better to do. They were doing it because they were desperate. Because the computing power they needed to do genuinely important work simply didn't exist anywhere else at a price they could afford. The demand was already there, it was just hidden. Look at it like this. NVIDIA wasn't creating a market from scratch. What they were actually doing was revealing a hidden market. And then crucially, they committed to it completely. This is the part that often gets overlooked in the NVIDIA story. It wasn't just that they made CUDA, it was that they kept investing in it year after year, even when the returns were modest. Better developer tools, better documentation, community support, university partnerships, consistent updates with every new chip generation. They basically decided to treat scientists and researchers the way software companies treat their developer communities, with genuine support, genuine resources, and genuine respect for what those communities were trying to do.
And the reason for that is because our company's mission is to solve computing problems that are barely possible. And so you want to attract amazing people who want to invent this new form of computing and apply it to solving some really difficult problems.
Yeah. And that community began to grow. Slowly at first, then less slowly, and then around 2010, something happened that nobody, not even NVIDIA, had quite anticipated.
What an amazing year is because of artificial intelligence. AI.
Machine learning researchers, the people working on artificial intelligence, discovered that training neural networks was, at its core, a massively parallel computation problem, and CUDA-enabled GPUs could do it dramatically faster than anything else available. We're not talking incrementally faster, we're talking 10 times faster, 100 times faster in some cases. Suddenly, experiments that would have taken weeks could be run overnight. Research that was previously too computationally expensive to even attempt became viable. Like, think about this for a second. Technology that was developed for gaming, for shooting at funny little fake 3D sprites on a 2D screen, is now being used to push humanity forward at a faster rate than ever seen before. We're talking biomedical research, climate data, fluid simulations, designing building, the aerodynamics of cars, the material science holding up motorways and bridges, and even space exploration, all from wanting better and faster running video games. Absolutely mind-blowing. In 2012, a neural network called AlexNet won the ImageNet competition, a global image recognition challenge by a margin so large it basically ended the debate about whether deep learning was the future of AI. It ran on 2 NVIDIA gaming GPUs, the GTX 580. This ferocious little beast featured NVIDIA's Fermi 2.0 architecture, sporting a 40 nanometer process, 512 CUDA cores, along with 1.5 gigabytes of GDDR5 VRAM, and had a max power draw of 244 watts. Those numbers may sound cute in comparison to today's standards. For example, the RTX 5090 features over 21,000 CUDA cores with a whopping 32 gigabytes of GDDR7 VRAM. But remember, at the time, this was a high-performance, record-breaking technological marvel. It was this GPU training, AlexNet, in 2012 that sparked NVIDIA to pivot from solely consumer graphics to launching dedicated data center cards that would progressively evolve to become the A100s and H100s we hear about today. But it was from that record-breaking moment that deep learning and NVIDIA became essentially inseparable.
GeForce enabled AI to reach the masses. And now, AI is coming home to GeForce.
And the crazy part, these specific NVIDIA GPUs that were used for this challenge weren't even designed for deep learning. Remember, all this parallel processing basically stemmed from wanting to render game worlds faster and faster. Deep learning, as we know it today, barely existed when CUDA was created. It was CUDA's parallel processing architecture happening to be exactly what deep learning needed, which was the right tool at the right time, almost accidentally. And here's where the really clever bit comes in. And this is the part that competitors have been tearing their hair out over ever since. Because CUDA was the dominant platform for so long, the entire AI research community built their work on top of it. Libraries, frameworks, tools, academic papers, tutorials, entire university courses. All of it built around CUDA, which means switching to a competitor's platform isn't just a matter of buying different chips. You'd have to rewrite your code, retrain your team, abandon tools you've spent years building expertise in, and lose compatibility with a research community that the rest of the world is building on. It's what's called a network effect, and it's genuinely one of the most powerful forces in technology. The more people use CUDA, the more valuable CUDA becomes. The more valuable CUDA becomes, the more people use it. For example, AMD has HIP and Intel has One API. They're not bad platforms. They're genuinely capable in many respects, but they were years behind. And in software ecosystems, years behind is almost impossible to overcome, not because the technology isn't good enough, but because the community isn't there yet. And communities, once established, are extraordinarily sticky. Let's talk about what this actually looks like in numbers, because I think it's the clearest way to understand just how completely the world shifted. In 2020, NVIDIA made about $10 billion in revenue. Genuinely impressive for a chip company, comfortable and very respectable. In 2023, they made $60 billion. 1 year later, analysts were projecting north of $120 billion.
Billions and billions and...
That is not normal growth. That is a company whose product became almost overnight the single most critical piece of infrastructure in the most important technological shift of our generation.
I can't wait to see my first rocket launch.
When OpenAI trained GPT-4, the model that sits behind ChatGPT, it ran on NVIDIA GPUs. When Meta trained Llama, when Google trained Gemini, when Amazon developed their AI infrastructure, the answer was always NVIDIA GPUs. Microsoft has spent tens of billions of dollars on NVIDIA hardware. Google has, Amazon has, Meta has. Every company that is betting their future on artificial intelligence is, by necessity, also betting it on NVIDIA. Their flagship AI chip, the H100, costs somewhere between $30,000 and $40,000 per unit. Yes, that's right, per unit. And companies can't get enough of them. There are waiting lists. There's a gray market where people buy and resell them at a premium, like their limited edition trainers. Microsoft, Google, Amazon, companies worth trillions are scrambling to secure supply of NVIDIA chips because without them, they genuinely cannot build the AI systems that are central to everything they're doing. Now, taking a step back and looking at the bigger picture, that is not a normal market dynamic. What it actually looks like is one company having captured something so fundamental that the rest of the industry revolves around it. NVIDIA currently holds somewhere around 88% of the market for AI accelerator chips, which for context is a more dominant market position than Google has in search, more dominant than Apple has in premium smartphones. And get this, even more dominant than Meta has in the market for online social media, and that's taking into account all of their social media apps and websites. Wait, let me check that again. Yes, that's including Facebook, Instagram, WhatsApp, and Snapchat. It's one of the most concentrated market positions in modern technology history, and it all came from a decision made in 2006 when they were trying to figure out how to grow beyond gaming. All right, so let's step back again for a second because I don't want to leave you thinking this is just a story about a company getting lucky. It really isn't. There are a few things happening in this story that I think are genuinely worth sitting with. The first is the idea of invisible demand. Jensen Huang and his team didn't look at a market that existed and work out how to serve it. They looked at a problem that existed, a deep structural problem in computing, and they made a bet that solving that problem was worth the investment even before the demand was obvious. That's a fundamentally different skill to just building a better product for an existing market. The second thing is the compounding value of ecosystems. CUDA isn't more valuable than AMD's alternatives because it's technically superior in every measurable way. It's more valuable because of everything that's been built on top of it. The libraries, the frameworks, the communities, the institutional knowledge. This is something you see again and again in technology. Often the product that wins isn't the most technically brilliant one, it's the one that became the foundation layer earliest. VHS over Betamax, Windows over other operating systems, QWERTY keyboards. What I'm trying to say is that once something becomes the default, changing the default has costs that go far beyond the product itself. And the third thing, and this is perhaps the most interesting, is the role of timing. CUDA didn't cause the AI revolution. The ideas behind deep learning and neural networks had existed for decades. The breakthroughs in algorithms that made modern AI possible came from researchers in universities. What CUDA did was make those ideas practical at a moment when the field was ready to move. It removed the computational bottleneck at exactly the right time, which meant that when deep learning went from a promising academic idea to a world-changing technology, NVIDIA was already embedded into the infrastructure of everyone doing the research. There's a phrase I keep coming back to when I think about this story: infrastructure precedes demand. The railways were built before most people had anywhere they needed to travel to. The internet was built before most people knew what they'd use it for. CUDA was built before most people understood that AI would need it, and in each case, building the infrastructure created the conditions for the demand to arrive. That's what NVIDIA did in 2006. They didn't predict the future perfectly. They just built something useful, committed to it fully, supported a community around it, and then had the patience to wait for the world to catch up. So the next time you see Jensen Huang pulling a graphics chip out of an oven in his signature leather jacket, grinning like someone who's just won the most unlikely bet in Silicon Valley history, just remember that the showmanship isn't the full story. The story is an engineer who looked at a problem most people couldn't even see, made a bet that most people thought was wrong, and then had the discipline to keep showing up and building quietly for nearly a decade before the world understood what he'd actually done. That's the chip that saved NVIDIA. And in a very real sense, it's also the chip that made the modern world of AI possible. Currently, NVIDIA has actually flipped the script on Intel and AMD with the advent of their new RTX Spark laptops featuring a super chip made for extreme AI performance. Ironically, it's basically an APU on steroids composed of NVIDIA's own 20-core CPU with integrated graphics featuring over 6,000 CUDA cores. Who would have thought this was the way it plays out? All the way back in 2006. And on that high note, thank you for watching. If these are the kind of stories you're into, engineering marvels, technological success, financial battles, the decisions that shape the world we live in, then do consider subscribing and leaving a like. Oh, and feel free to leave a comment as to which revolutionary technological breakthrough or maybe engineering fail you want me to talk about next. For now, I'll catch you or you'll catch me in the next one. Take it easy.